Calculation of electric flux is very important for a class 12 student. Not only for your all competitive examination, it's a conceptual part for your board examination also. So understanding calculation of electric flux and later on magnetic flux is a very important topic for you. Past session I have explained in details how to calculate electric flux through a closed surface and through a plane surface. Curved surface also indeed I have explained how to take the projection. Today's class I will be discussing more problems where some problems in the beginning designed for understanding, that is helpful for your board examinations, and some problems concept required for your any competitive exam like JEE, NEET, WBJEE, whatever. So let us start explaining calculation of electric flux in some more cases so that you can apply it in solving more difficult sums. Before I start, I just remind you the formula for calculating electric flux. This area vector is there. Area vector direction is what? Hope all of you remember it. Area vector is perpendicular to the surface always. The ds vector is nothing but magnitude of area multiplied by n cap. N cap is the unit normal drawn to the plane of the loop. If electric field vector, let me discuss the general case only. If electric field vector makes an angle theta with the direction of area vector, then d phi or phi equal to, just on a small portion if you consider, the small area if you consider, then d phi equal to E dot ds, dot product between electric field vector and ds vector over the whole surface area. If you want to find, then phi out is going to be phi out phi in by the same formula, surface integral of E dot ds. Okay, this is circular area, and in case of that if there is a closed surface, I showed you how to calculate electric flux by taking elemental portion and then by summing all those portions by integrating. Let us take the first example to remind you the concept again. A charge q is placed at one of the vertices of a square of side A as shown in figure. Find the flux through the square. Where is the figure? I did it for you. This one is a square of side A. Find the electric flux through the square. If the charge q is kept here and the square also lie in the same plane, then you know field lines due to this charge, if you go for symmetry, then charges you know radially outward for a point charge, and number of charges depend on what? This factor already explained to you before in calculation of electric field strength, that field strength depend on number of fluxes, and number of fluxes coming out from a charge depend on the magnitude of the charge. Greater the magnitude of charge, number of lines of forces coming out of it also will be greater. But see, in this construction, if you consider all the fluxes passing through this surface, then those fluxes are parallel to the surface. So for this square, if A is the length of side, then area vector you can write A square into n cap. N cap is the normal coming towards me, and electric field vector along the plane. That electric field vector is, all those lines of forces parallel to the square plate. So if we try to calculate the flux, then we have to remember the direction of E. E is in the plane of paper. So E vector can be taken as, we can take it as Ex I cap plus Ey j cap. I cap and j cap, I am assuming that they are unit vector along x and y axis. This is I cap and this one j cap along x axis and along y axis. Now this area vector, unit normal is coming towards me. So obviously n cap can be replaced by k cap. So area vector going to be a square into k cap. If you find E dot A now, just use dot product. Whatever electric field is there at any point, that Ex I cap plus Ey j cap, at any point if electric field strength given by this dot A square into k cap. This k cap vector is there, which is normal to the plane of this area. So this is going to be Ex A square I dot k. What is the result of I dot k? This you know very well. They are perpendicular to each other. So dot product will be 0. J dot k is also 0. So Ex A square 0 plus Ey A square 0 is there. So E dot A going to be equal to 0. Alright. So flux phi to the circle area will be equal to 0 only. A charge q is placed at center of a sphere of radius r. Find the total outward flux through the sphere. So where is the sphere? Let me consider this diagram here. Okay. Last class I have taken a heavy object in a uniform electric field. That was spherical, not a perfect sphere. So this time it is a perfect sphere, but not placed in a uniform electric field. Charge q is there. The charge q is placed at the center of the sphere. Then you have to find total outward flux. We will be using the method I have already explained. Take an elemental portion here. I mean at every part, this one is the elemental portion. Electric field lines are radially outward. This is already explained. These field lines will go this manner. Here, this way, coming out, not getting in. It is coming out. So electric field due to this area is radially outward. Let this field be E1 and this one be delta A1. Similarly, we take another elemental portion here. I mean very small part. We imagine the surface area of the sphere divided into many parts. Then due to those parts we are going to calculate electric flux. This area be delta A2. The field line is going outward like this. Let this field vector be E2. This field vector we are assuming E2. So the flux due to this can be calculated, that this is E2. Similarly, we take a small portion at every part on the surface, then we add all these. So what is the flux passing through this portion delta A1? That phi 1, delta phi 1 will be equal to E1 into delta A1. You know that E1 is what? The electric field strength. A1 is what? Delta A1 vector is what? The area vector. E1 and delta A1, they have the same direction. So this is going to be E1 delta A1 cos 0 degree. You understand? Similarly for this portion, this area delta A2 we have taken here. Due to this, outward flux del phi 2 going to be equal to E2 into delta A2. This is going to be E2 delta A2 cos 0 degree. So it is E2 delta A2 only. This one E1 delta A1 only. Now this charge Q is placed at the center. If the radius of the sphere be R, then this magnitude of E1 and magnitude of E2 will have the same value. And this is given by Q by 4 pi E0 R square, you know. Take the elemental portion on other sides also. I mean, it has surface area. Due to this surface area, surface elements are there everywhere. And you calculate electric flux through all these portions. Okay? Take area this portion also. I mean, so many are there, we cannot draw all. But you have to keep in your mind that the value of E1, E2, whatever you take on the surface, this is equal to electric field Q by 4 pi 0 R square. At every point on the surface of the sphere, electric field is given by Q by 4 pi 0 R square. So when you take an arbitrary element, suppose this is our arbitrary element delta AI, and electric field vector is going this manner, which is EI. Then EI delta AI also they have made the same angle. So delta phi I will be EI delta AI cos 0 degree. So it remains the same, that is EI delta AI. So how to calculate net flux? This is the representative of all those elemental portions. So net flux coming out will be summation of delta phi I. This symbol I have already used, I equal to 1 to n, and this n is tending to infinity. So this is limit n tending to infinity. If you don't take limit, it doesn't matter. You have to write the answer only. Don't worry. If you are not habituated with this, you just write EI delta AI, which is nothing but integration of E into delta A over the whole surface. E has this value Q by 4 pi 0 R square. For all parts, they are all lying on the surface of the sphere. So electric field strength has this value only Q by 4 pi 0 R square. E you take outside, integration S delta A. What is the value of E? It is Q by 4 pi 0 R square into 4 pi R square. 4 pi get cancelled, R square and R square also get cancelled. This is going to be Q by E0. So net outward flux through this surface is going to be Q by E0. Okay? This is very important observation, and I am telling you that if you keep the charge anywhere inside this closed surface, flux will remain the same. It is stated in Gauss theorem. Gauss theorem we will do in next class. I will explain in details. But this is introduction. Any charge you keep inside a closed surface, the total outward flux is coming to be equal to charge enclosed. We replace Q by Q enclosed, and phi out is given by Q enclosed divided by E0. Okay. Cylinder of radius R and height h is placed in uniform electric field of strength E. Calculate electric flux entering the cylinder if the axis of the cylinder made inclined an angle beta with the vertical. First part, where it stands vertical, already done in this class. In this case, flux linkage, you remember, I hope all of you remember this. In the first session only I have explained that electric flux, for the electric flux, which part is responsible? The part of the cylinder which is actually perpendicular to the direction of field lines will account for this. Okay. we have taken this area only, where h is the height and r is the radius. So diameter is 2r. We have calculated phi equal to, E into 2r into h. We did this in the past session. But now the problem is different. The sphere gets inclined now. Someone has rotated the, not sphere, it is the cylinder. Someone has rotated the cylinder by an angle beta. Beta with what respect beta? If we draw this axis of cylinder, this is the axis of cylinder. This axis of cylinder will make an angle beta with the vertical now. Okay. Initially it was straight. Axis of the cylinder was along the yellow line. Now it is inclined. So axis of the cylinder is also inclined. Okay. This angle is beta. Your problem is to calculate outward flux. If we go back to the previous sum, there was no flux linkage to the end caps. Why? Because area vectors are perpendicular to the end caps. Area vector here, if you consider, this is the direction of area vector. Okay, this is ds and this is the direction of electric field. The angle between these two directions 90 degree. So no flux can pass through the end caps. Similar is the case for the opposite end cap. But here flux will pass through the end caps. In both the end caps, just go through this portion also. Okay. In both the cases, here and here, it is the angle beta. It is rotated by an angle beta axis. This is the axis of cylinder. You can see this axis of cylinder joining these two red points get inclined by an angle beta with the vertical. It is situated in uniform electric field of strength E. Your problem is to calculate flux linkage. So how do we account for this? How many surfaces responsible? This time flux will pass through the end caps also. Am I right? Where are those end caps? This is one end cap. Suppose the surface area of this end cap is S1. This one surface area is S2, although they have the same value, but let me write in the beginning. And this one, this 2R H portion, I have explained, this part is 2R and this part H. 2R H is inclined. What way it is inclined? Area vector will be directed in what manner? This is very important here. That area vector perpendicular to the area only, it will go this way. Isn't it? Not that arrow pointing inward. Arrow will point outward only for the area vector. Okay. So, this area I am taking S3. So, what is the angle S3 made by with the vector E? That is going to be beta. Because initially S3 vector was along E. Now it is rotated by an angle beta. So, this angle is also beta. So, net flux passing through the cylinder in this case going to be flux due to surface S1 plus this is phi in or phi out. I must phi in. Phi S1, phi S2 and phi S3. Phi S1 will be what? This is area vector. Area vector is S1 vector. We have taken this way. And here area vector directed in what manner? You all can see that similar way only. I have drawn the diagram already. So this is S2 area vector. S2 area vector will make what angle with beta? Will make what angle with E? That is also beta. I mean, not with E, it is beta, it will be 90 minus beta. This angle is 90 minus beta here, you can see. And this angle is also that vector making an angle 90 minus beta with this, with the direction of electric field vector. Alright. Now we have to count all these. As I want to calculate the flux entering the cylinder, so I need to take this angle 90 minus beta, but this one beta only. This area already I told you, if height is h and diameter is 2r, so phi s2 going to be what? This phi s2 will be area 2r into h, and angle between s3 and E vector is beta. So dot product of these two will give you 2RH E cos beta. Phi S1 is what? That is pi r square. The area of this circular region, pi r square. It will be pi r square into E, and the angle between them is 90 minus beta. So it will be cos plus this. Here also it is. We are calculating inward flux. So pi r square E cos 90 minus beta. So this is going to be pi r square E sin beta in two cases plus 2RH E cos beta. Okay. So just add these two, we'll get the result. You understand, I hope? A very long uniformly charged thread oriented along the axis of a circle of radius r rests on its center with one of the ends. Charge of the thread per unit length is equal to lambda. Find flux of electric field vector E across the circle area. Case may be a bit complicated. Let us draw the diagram first. So let us take this one as the charged thread, infinitely long charged thread. You know the strength of electric field at one extremity. This we have discussed in past. In one of the session I showed you, if this one is a charged thread, then at one extremity the strength of electric field has two directions. This distance VR, then one field will be directed this way. Field has two components here. One is along x-axis, the other one is along y-axis. And you know the magnitude of this. If the line density of charge is lambda, electric field is here lambda by 4 pi E0r, and this field is also lambda by 4 pi E0r. I am not talking about resultant field. Why? This we will understand. So due to this charge thread also, electric field will be on this circle area. It is going in every direction. If we consider this part, it is going this way. At this is an arbitrary point. Say. On the whole circle area, it will happen. The electric field, one electric field is directed this way. Electric field has two components. One is along x-axis. It is given by Ex equal to lambda by 4 pi E0r. Here also Y equal to lambda by 4 pi E0r. Isn't it? So any point on the circle area, if you consider, the component along x-axis has no role to play. Electric flux, what is the area vector of this circle area? You draw the area vector. Area vector is what? A equal to pi r square. If the radius is r, it is pi r square, and this direction we are taking, suppose y-axis this way, so it will be j cap, pi r square j cap. You know, area vector has a direction. This time it will be along y-axis. We are choosing x-axis, y-axis this manner, x-axis horizontal. So area vector pi r square j perpendicular. This Ex is perpendicular to this area vector. Ex is along x axis. If you write I cap, that will be better. Ey is multiplied by j cap because it is along y axis. So which component of the field is responsible for calculating net flux through the circle area? Not Ex. It will be Ey. Isn't it? And the flux passing through the circle area phi out is going to be equal to Ey dot A. As both are expressed in terms of J, we need not write cos theta over there. Ey value put lambda by 4 pi E0 R. But the problem is, if you calculate Ey this manner, are you going to calculate for only one point? No. Then that Ey, when you are calculating, it will not be same for the whole surface area. You have to take an elemental portion of this area over there. That elemental portion I am drawing here. This is the elemental portion. Okay. Elemental portion, it has radius same as before. I told you radius is r. So that radius we are going to take r only. Okay. Radius of that circular part is r only. And its thickness, you assume that thickness is equal to dr. I am not drawing the whole diagram. This elemental portion, it has area pi r, 2 pi r into dr, because dr is the thickness. So elemental portion, this is the elemental portion where you imagine that ring is, this circular region is divided into infinite number of parts. This is the elemental portion. Its area will be circumference multiplied by dr. This is dA vector. So this will be dA. So if you write Ey into A, it will be wrong, because over the whole circle area, Ey will not remain the same. It depends on distance. I have written here, depend on distance r. It is true for the whole circle at the extremity. But if you consider at a distance r, smaller we have taken, no, it will be lambda by 4 pi 0 smaller, lambda by 4 pi 0 smaller. So Ey going to be what? Ey into dA. Remember this? dA also vector. dA vector is also along the direction of j cap. What is dA vector? Let me write. dA vector is going to be 2 pi r dr into j cap. Okay. So you write Ey first. Lambda by 4 pi 0 r j cap dot 2 pi r dr j cap. Clear? So r getting cancelled. It will be lambda by 2 E0 into dr. Am I correct? Lambda by 2 E0 into dr. This is d phi. d phi out through the elemental portion. So net flux coming out, now calculation is very easy, just integrate. So phi out going to be equal to lambda by 2 E0 integration over the whole surface. Whose integration? dr, all these elements will be added. It will be from 0 to r. We have taken the radius. It is given the radius is bigger. So it will be lambda by 2 E0 multiplied by r. Clear? Understood? This is another very good question in this range. Point charge Q placed at origin. Find the flux of electric field produced due to the charge through a circle of radius r lying in yz plane. Okay. You take this one x axis, this is y axis, and this one z axis. Okay. a point charge Q plus Q we are taking kept here at the origin. Find the flux of electric field produced due to charge through a circle of radius r yz plane. It is lying in yz plane. So your problem is to find the flux of electric field on this circle area. Okay? This is not a simple problem. Why? Because if you take an elemental force, if you take any point here and join Q to this point, then electric field here is directed this manner, radially outward, isn't it? So on this circle area, when you are going to find electric flux, you have to take care of this part. At every point, field direction is different. So at this point, if we take electric field as strength as E, then if we take a small area, it will be EdA into cos theta. That area element may not be directed along the direction of field. Area element is always perpendicular to the surface. So think what you are going to do to find the flux. Again, the problem will be like that, where we need to get an elemental portion where every point on this elemental portion electric field strength will remain the same. See, electric field strength, based on this angle theta here. Theta is angle with y-axis here. If you take point here, the strength of electric field changing because of distance changing. One can say that it is because of the angle with y-axis changing. So you have to take care, you have to divide in such a manner that on elemental portion at every point, the strength of electric field and direction remains the same. So the elemental portion going to be a circular region. You can see that this circular region, if you consider this 3D view, this circular region, it is oriented in such a manner that from any point on it has the same distance from the origin, isn't it? Here also field going directed this manner, radially outward. So this is our elemental portion. We are taking the center of the circular portion with origin as the initial line. From here it is rotated by an angle theta to reach the elemental portion. Elemental portion has radius r and its thickness be dr. We are assuming the thickness of the elemental portion is equal to dr. Got it? This we are taking thickness, we are taking as dr. Distance from origin be x. Then the ring, on this ring, any point is at a distance r dashed, that r dashed square will be equal to r square plus x square. So r dashed going to be under root r square plus x square. And through this elemental portion, how many field lines are passing? That you have to get by the same formula. d phi equal to E dot ds. What is electric field strength here? This distance is r dashed. You all can find electric field strength here. Strength be E. E directed this way. But area vector perpendicular to the area along this direction. Area vector directed along this direction. N cap this way. Electric field vector this way. This angle theta. this also will be equal to theta. So for this elemental portion, area of the elemental portion, let us write dA equal to area of the elemental portion. This is going to be 2 pi r into dr. This is dA, area of the elemental portion. So d phi, flux passing through this elemental portion, will be equal to area, that 2 pi r dr, into component of electric field vector along area vector in cap, I mean unit normal, is E cos theta. So just substitute the value. It will be 2 pi r dr into E. What is the value of E? Distance is r dashed. So the strength of electric field you can write Q by 4 pi 0 r dashed square. So E value you put Q by 4 pi 0 r dashed square into cos theta. Cos theta is what? X by r dashed. Understand? So d phi equal to, let me simplify this expression first. R is variable. This 2 pi and 4 pi get cancelled. X is constant. X by 2 is 0. Qx by 2 is 0. R dr by r dash square into r dashed. It will be r dashed cube. Got it? R dashed value I have written there. So net flux to the surface will be integration over the whole surface r dr by r dashed cube. What is r dashed here? R square plus x square to the power half. So there it will be r square plus x square to the power 3 by 2. Clear? And this r is variable. At the center value of r is 0. At the extremity it will be r. Clear? So it is integration problem now. How do we integrate? Let us take r square plus x square equal to z square. So 2r dr, after differentiation it will be 2z dz. R dr equal to z dz. So this part, indefinite part, if we find r square plus x square to the power 3 by 2, r dr value is z dz by, this is z square to the power 3 by 2. So it is dz by z cube. No, z by z cube. So dz by z square, its integration is minus 1 by z. What is that? Z is what? Root over r square plus x square. So minus 1 by under root r square plus x square. Now go on finding its value. Just put it there. In the integrand, if you put this value here, it will be qx by 2 is 0 and minus 1 by under root r square plus x square 0 to r. So qx by 2 is 0, put the upper limit, r square plus x square plus lower limit under root x square. So value is qx by 2 is 0, 1 by x. So answer will be q by 2 is 0, 1 minus x by under root r square plus x square. Okay. This I am doing by integration today. We will do it by another method in the next session, where the concept of solid angle plays vital role. But again I will tell you, this method is also useful. It matters in your student life. You need to learn calculation of flux by this method also. Okay. This number 6 I have taken from the problems in general physics by I.E. Irodov. Okay. Why? Does it have any link with the previous sums? Of course. But here you have to see that 2-point charges Q and minus Q are separated by distance 12. You have to find the flux of electric field strength vector across a circle of radius r as shown in figure. So this is the diagram. Plus Q minus Q is there. This circle area is placed in between these two. Its radius is r. You have to account for flux passing through this. Do you find any similarity with the previous one, where a charge Q was kept at the origin? Of course there is a similarity. But this time two charges are there. Due to one charge, calculation will be same. You will take some elemental portion here. Then you find the flux linkage through the elemental portion. Elemental portion is a circular region. That field vector will be directed this way. You will take the component. You will find the flux by the same method. But what about the contribution of minus Q? Charges from Q are going out. Field lines are going out, and due to this, field lines are again going out in respect of observer standing here, because field lines will be originated towards the charge minus Q. Okay. So strength of electric field will have the same, will be directed towards the charge. If this one is E1 due to the charge 1, then E1 will be this way, E2 will be this manner. To find the field, we observe that a component of it, if this angle theta, by symmetry this is also theta, then a component E1 sin theta due to E1 will be directed this manner, and due to this one, that E2 will be directed this manner. It is E2 sin theta. Okay. So E1 cos theta and E2 cos theta will be passing through this circle. But what is E1, what is E2? The problem made simpler by stating that distance is L and it is kept distance is 2L and the circle area kept midway. So this part is L, this part is also L. So the magnitude of E1, magnitude of E2 will be the same. If you take this one smaller, this is going to be R square plus L square. Here also it is going to be R square plus L square. So this has value Q by 450, Q by 450 R square, it will be R square plus L square. Okay. So E1 into same thing. We are assuming that this is equal to E. So this part going to be 2E cos theta. Am I clear? It is going to be 2E cos theta. So the difference between previous sum and this sum is here, that when you find the flux to the elemental portion, you find d phi equal to what? D phi, the way you have taken, it is area of this elemental portion is 2 pi r dr. This multiplied by 2E cos theta. So only factor 2 is coming into consideration. Rest is similar. I am not going to do. Just the result you got here will be multiplied by 2. It will be 2q by 2e0 1 minus x by root over r square plus 6. All the best to try at home, complete the sum. Okay. Now this is another very interesting problem. Electric field strength depend only on the x and y coordinate according to this law, where A is a constant, I, J are unit vectors along x and y axis, Find the flux of electric field through a sphere of radius r with its center at the origin of coordinates. Okay. So in this three-dimensional coordinate system, this is x, y and z. If we take E equal to this thing, and if we say that E is running parallel to the, tangent to the surface of the sphere, will be wrong. Direction of electric field has to be radially outward, isn't it? So electric field always radially outward here. So take an elemental portion here. Electric field given in this form only, that is E equal to, E vector is a constant A multiplied by xi plus yj by, you can say that this is the unit vector, because modulus of this thing going to be 1. So electric field is actually A into this n cap, and this is the direction of unit normal also. So angle between the electric field vector and area vector, if you take ds, that portion ds is equal to ds multiplied by n cap, and this is also n cap, A multiplied by n cap here. N cap is the unit normal perpendicular to this point here. This is unit vector, no? So unit vector, they are directed this way only. Only thing I'll do here, I'll be changing the x coordinate here and y coordinate, z coordinate here. That's fine. So ds is ds into n cap, d phi going to be equal to E dot ds. This is ds multiplied by n cap into a n cap. This is a into ds, n cap dot n cap equal to 1. So phi equal to integration a ds over the whole surface. A is a constant, come out, ds. The radius of this sphere is taken as r. So it will be a into 4 pi r square. It is 4 pi a r square. Clear? So I hope you have understood flux calculation in these few cases without using Gauss law. This method is equally important. As you need to learn Gauss law, you need to learn this method also as a very good student of physics for class 12. Okay. See you in the next session with Gauss law and calculation of flux with the help of solid angle. Thank you.